I'll go right into the matter. I'll start with a bit of a look back in history to explain sort of trends of what went on in the past decades, I guess ever since World War II. And I'll then do a zoom on 3 technologies to explain the balance or the evolution between the power of knowledge versus the power of data in AI technology. I'll speak about text-to-speech systems, I'll speak about dialogue systems, and about computer vision systems. And then I'll give you a bit of an overview of what can be done in AI today. So being done with the retrospective, we'll focus on what can be done today. And after that, in chronological order, I'll speak about the future, maybe. Right, so let's see if everything works, but I think it does. Right, early on, from after World War II, so from the moment on where computers started to be modern computers, so where they started to be electronic devices as opposed to electromechanical devices, computing, the science of computing, of building computing machinery, was very narrowly sort of wed with artificial intelligence. And people making computers were also people who started thinking about, well, artificial intelligence as in intelligence demonstrated by machines. So what you see here is, this is in the Cambridge Computer Lab, which at the time was called the Mathematical Laboratory. This is one of the, I think it's the second modern computer after. So this is EDSAC and this is ENIAC in the US, which was built in 1948. This is 1949 or so. And both are the first examples of computers with stored programs on them, where data and program lived on the same support, right? This instead is to remind us that, well, the beginnings of computing, we owe to the effort and the investment, I mean the money invested, is largely due to well, the military and the war, as a matter of fact. And so this is, maybe some of you have recognized it, it's the Enigma machine. It's a ciphering machine, which is derived from a commercial thing. In the beginning, the Enigma machine was used in the German submarines, in the U-boat during World War II. And this machine was derived from a commercial, say, product that had been developed in Germany in the 1920s, had been adapted for military usage. And then what happened in during World War II was that many people, including Winston Churchill, were sort of very keen on the activity of their cipher bureau, so decrypting secret messages. And that's when they put Alan Turing at work in Bletchley Park. The bomb is a machine, essentially was, probably filled this entire room here. It's not a machine like these ones, it's an electromechanical machine that was able to decipher messages ciphered by this machine, which is a very simple machine. It's a machine that's like a typewriter, essentially. Decipher these codes in a couple of hours due to statistical properties and, in fact, statistical defects of the way this machine encodes its messages, okay? So that proved that, I mean, that's a very important idea for later on. So statistics and sort of probabilities were used very early on in these machines, and in fact, it's no surprise that Alan Turing was the one at work on this, and he worked on these statistics and probability so properties of ciphers, ciphertext, and so forth, which would then be used in machine translation. So these were also the years when, so this is Alan Turing, and so this is an article, the very famous article by Alan Turing. It's a 1950 publication. He describes, well, he poses the question, that's 1950, right? I propose to consider the question, can machines think? And the tests that the sort of test that he proposes is still sort of in use nowadays, and sort of a respected benchmark for whether a machine is intelligent or not, and it's called the Turing test. And it's a test in which essentially you put a machine in a dialogue with humans, and you let humans decide or assess whether the thing they're dialoguing with is a human or a machine, simply by asking questions and having an interaction, right? So it's a sort of extrinsic evaluation of intelligence in a way, right? So it's like the thing that you're interacting with is a black box, and you have to decide whether it's intelligent or not. And there are tests. So one is called the Loebner Prize, which actually run like this. So you have panels, judges, humans, normal humans, and they interact with machines and they decide, whether this thing is a dialogue, a sophisticated chatbot, or whether it's a human. All this is to say, early on, this guy and others like him started thinking that the things they were building could have immediate bearing on the future of AI. And the same was reflected in science fiction. So this is Isaac Asimov, and this is the famed 3 laws of robotics. And I think, personally, I think that science fiction is a great way to play out scenarios. So I think it's an integral part of, say, futurology in a way. I think it's very important. That's why I put the slide here. And so the 3 laws of robotics, I think that's also 1950 or so. I should look up my notes, but I think I'm about right. I couldn't, obviously I couldn't resist having the, for those in the know, this is Space Odyssey. This is the Stanley Kubrick movie. So this is 1968. There's this famous scene where HAL decides for what it judges to be the greater good, to sort of not open the door of the pod to poor Dave, who's left floating out in space. 1950s, 1960s, these guys were really believing that they were onto something. And these high expectations were also at play in research proposals. So this is also a very famous sort of milestone in AI history. He says, he writes, "We propose that a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956 at Dartmouth College. It's to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it." Okay, then he goes on to say, what we will tackle in these 2 months, group of 10 people, 2 months, doable. Automatic computers, language processing, artificial reasoning, and other things. So that's to say, yeah, a 2-month project, we'll have done it, and then, we'll move on after that. A similar thing was this other proposal, which is this is a thing by it's a research proposal, or it's an endeavor. This guy is called Warren Weaver. It's a 1949 proposal that he made to say, essentially, let's fund research in machine translation. In a couple of years, we should be able to automatically translate texts. And the way I propose to do it is like this. This is, so when I look at an article in Russian, obviously, Cold War Russian to English translation. When I look at an article in Russian, I say, this is really written in English, but it has been coded in some strange symbols. I will now proceed to decode. Okay? So here you immediately see the tie to what Alan Turing was doing. And in fact, the kind of thinking that was behind here, and that was only picked up much later than the 50s, the kind of probabilistic approach to machine translation, this then only started in the 90s. And in the very beginning, what they had to do were rule systems. And so there was a demonstration of this system in New York. They did this demonstration of a translation system which was built on rules. So it was built on a system that had, like 10 or so grammar rules, had a vocabulary of 250 words, and the demonstration proceeded to, have sort of like 50 carefully chosen sentences in Russian translated to English. I'll take the opportunity to tell you what this gradient of colors is to mean here. Repeatedly in my talk, I'll try and situate the sort of technology or the approach that I'm speaking about by situating it on this gradient. And the idea is that on on the left here, what I want to have is methods that make intensive usage of knowledge. And by that, I mean things like that's in the head of a domain expert. So typically things that can be encoded in rules. And here, I'll have the other extreme of the spectrum, which is data. Things that can be learned and that don't require experts to produce, to explicit knowledge about their domain, okay? This is entirely learned. This is sort of hard-coded. So repeatedly, I'll go like, oh, we're somewhere here, or no, this is totally a technology that's on the knowledge side. It's totally rule-based. Or in the opposite, maybe this does not know anything about the domain. It's entirely learned from data, and then will be on this side of the scale, okay? So this system here is totally on this end. It's totally hard-coded, and it doesn't know anything about words, actually. Okay, it's just a computer program that takes in strings and deals, according to these complicated rules, deals with the strings and replaces strings by other strings and so forth. This also is the reason why, all these things are the reasons why people started getting super optimistic about the following years, and they wrote things or said things like this here. This is Marvin Minsky, another great name of AI. And this is 1970. In from 3 to 8 years, we will have a machine with the general intelligence of an average human being. So that would be 1975 or so. And this is Herbert Simon, another great scientist. This is 1965. So this guy, right? Herbert Simon won both the Nobel Prize in Economics and the Turing Award, which is the sort of Nobel Prize in computer science, right? So this is not a loony, okay? He says, machines will be capable within 20 years of doing any work that a man can do. So within 20 years of 65, that puts us in 1985, okay? And so, yeah, great expectations for all these things. And obviously, great expectations haven't come out of trend. Here we have another luminary of our time. This is Elon Musk. And you can ask me, or I can tell you about what I think about these predictions. I think they're not spot on. And as Greek drama teaches us, after hubris comes catharsis. And so all these expectations were largely crushed after a couple of years. In the UK, it was a parliamentary inquiry that was led by this man here. This is Professor James Lighthill, a fellow of the Royal Society, professor of mathematics at Cambridge. He was commissioned in the 1970s to run an inquiry into the state of AI and what's going on. So he went on to speak with people who are working in the field and compare predictions with what had been produced and so forth. And he produced a report that was positively damning for the field. It was devastating, and essentially, then there were debates. You can watch the debates on BBC on the television. You can watch them on YouTube. They're super interesting, actually. Where he speaks, so Lighthill speaks with AI experts of his time and justifies why he thinks, there's strictly no reason to be very optimistic. Everything is going in the wrong direction, and we'll never get there, essentially. So this was 1973. This guy is Yehoshua Bar Hillel. He's a linguist by training and went on to do computer science. And this guy did about the same thing on his own, like research initiative. He was one of the early people who worked on machine translation. And he decided to look at whether machine translation would actually work. And he did this in the early 1960s. Then he wrote this paper to say, the title is, it says it all, a demonstration of the non-feasibility of fully automatic, high-quality translation. Produced a couple of examples. So for instance, he had this example here, the first here, that goes, the box was in the pen. And he says, because there's, you never know what pen means. Is pen this thing here, or is pen the sort of thing where you have where you can put dogs or babies according to taste? Because of word ambiguity, because of sense ambiguity, these are things that you can't encode in a way, and you can only resolve if you have strong knowledge of the world. Okay, if you understand what the world is, what the world does, and things being on top of other things, and physics and experience that only humans have, and so forth. So he says, no way we can code this into a computer, at least not soon. In the US, there was another similar report, the Alpaca Report. Alpaca stands for Automatic Language Processing Advisory Committee. National Academy of Science went on to do exactly the same thing, and they all said, no, that's not going to work at all. And this, in a sense, was a good thing for the field of AI, right? So it put a stop to a lot of funding. So a lot of money went away for research. But instead, what happened is that instead of having grand programs, people started to focus on narrow domains and started to try make things that work. So even if they were not grand and solving the general problem of intelligence, instead they solved small problems. And they started making these things. This is an example of a system called Mycin. It was written in Lisp in the early 1970s. And it's a system to diagnose bacterial infections, severe bacterial infections, and to sort of prescribe antibiotics. You know, find out what bacteria it is based on symptoms and prescribe antibiotics to kill the bacteria. And this is a sort of doctoral, like it's a dissertation, it's research. This thing here, this is the Delta Expert system. This was used in industry instead. It's a system to diagnose faults in diesel engines. Okay? So it's a system that you could interact with using a very primitive human-machine interaction consisting of essentially you could say yes, no, don't know, and help, or stuff like that. And that was it. It contained 500 rules, of which 200 just for help, for the help system, so 300 just for diagnosis. And it used rules like this thing here. So they're essentially complicated if-then rules, right? Where the if part, the idea was that the if part would elicit information from the user and find out, ask questions, and once you had the knowledge, then you could proceed to the then, and then you would say, for instance here, write fuel system faulty, probability or certainty 1.0. Comment establishes that there is a fuel system fault. So once you have all this information, you can conclude that there is this thing. And that's the kind of systems that were sort of used, developed, and trendy in the 70s and 80s. And another thing that these really bad reports for AI had as a consequence, and these expert systems, is the development of AI in industry. A big program for work on a machine called, it's no joke, called PIMP. Stands for, let me see, parallel inference machine, no, can't remember, programmable inference machine or something / parallel. The idea was that it was a machine built around Prolog. So it's a machine that allows to do inference in which you code rules like the ones we just saw, where you go from axioms, you start from axioms that you encode, and then you have the machine reason about the axioms and then draw conclusions, like do inference. Okay? This other thing is to illustrate the work of Ray Kurzweil, who started off his career, now he's at Google, and he started off his career in the sort of 70s, 78, by working on speech synthesis systems and optical character recognition. In the years after, so that's the 1990s, we had, after these expert system things, after this trend of expert system things, we started having systems that worked on statistics. And that's where the recent AI wave has its roots. It's in counting things, in working with large sets of data. So typically in natural language processing, you started having access to large corpora of text and being able to do counts on words, on expressions, on the occurrence of figures of speech and so forth. And in the 1990s, so you had this milestone article, which is called a Statistical Approach to Machine Translation. These guys invented support vector machines, purely statistical beasts, algorithms that were super trendy and successful in the 1990s. This is one of the a book by Vapnik, whose title says it, Statistical Learning Theory, so counting things and doing statistics and doing predictions that worked on average, but not always. This is another book that was published in the same years, which is a sort of continuation of expert systems. The author is called Julia Pearl, the ideas that he worked on are like, let's make these expert systems probabilistic. Instead of having hardwired rules, let's make these rules probabilistic, and let's draw inferences that may be uncertain, and that might reason about uncertain things in the inside. And that continues to be very current today, especially because current machine learning systems do not, are not able to reason causally at all, almost. And in about the same years, and in the same place, in fact, in a research lab of Bell Labs. This is a trend that I've not described so far, but that started also in the 1950s. This is a photo of the Perceptron, which is you see the wires, right? This is a hardware system that simulated connections between small reasoning things that were called neurons by analogy, sort of loose analogy with the brain. And this is a 1960s thing, the perceptron. And well, these people started developing the equations that would then make neural networks usable for the rest of the time. So until today, these same equations are used in neural networks. I'll explain very briefly to get everyone on board what a neural network is like, but I don't want to spend too much time because I want to tell you so many other things. Neural networks, as I said, they're loosely modeled on the brain. The idea of neural networks is that we have, so this is an input and an output sort of stream of things. What we do is we assign each pixel a grayscale value, so it's a number. All these columns here, we arrange in a single long column. Okay, so the entire image gets coded on these bubbles here. Each bubble holds a number. And then what happens to the numbers is that they get combined, they get multiplied and added together. And this is what all the wiring here denotes. So they get combined, new results, new intermediate results, and they get combined again, new additions and multiplications, another intermediate result layer, and then they get combined and combined again. And this is the output layer, it's called. And that says, according to the result, so it's made so that the numbers in the bubbles, in the nodes here as the output level, they're between 0 and 1, so between 0 and 100% or so. And they say whether the image in the input is more likely to be a 0, a 1, or 2, and so forth. So whether the image represents one of these digits. Okay? So it's merely a matter of addition and multiplication, what goes inside, and a couple more operations which turn nonlinearities, they're called. But that's not important to look into now. Okay? So it's a very simple being, and complex variants of this are still in use nowadays. PageRank. This is a bubble picture to illustrate PageRank. PageRank is the algorithm that the founders of Google started with, and that still is inside the Google website ranking algorithm. And the way it works is statistical entirely. It says if I click randomly from one website to the next, where am I likely to spend, to come back to spend most time in? What websites are the ones that have the most, both incoming links and are pointed to from popular websites and so forth. So it's a random walk algorithm, and it's trained. So you look at websites, you count links, and you look at data, in fact. Okay, so there's nothing here that is, as opposed to this project here, nothing in PageRank that is hardwired. This is the demos. It was a project that was started in the late 1990s. It was a kind of open directory for the internet. Maybe some of you remember that. They meant to sort of map the entire internet and have an index to it and a reason thing. So you had games, you had sports, you could go into baseball, and then you had different baseball websites, and everything was meant to be curated, a bit like Wikipedia and stuff. And in 2017, they gave up because the internet had grown so big that it wasn't feasible to do that anymore. Okay, so again, this trend is clearly going from knowledge-based systems to rule-based systems, from rule-based systems to data systems, simply because more data is available, because more computing power is available, and therefore because more can be done with them. There's even people to say that progress in AI today is only due to the availability of large data sets. Going from input to response, going from pictures to deciding whether the human face is in it is an application that's photo tagging, face tagging. If you have data that has an audio clip, you can do speech recognition from that data. What you need is a corpus like this, and you can do the task. If you have an English like many English sentences and their translation in French, then you can do language translation in a data-driven way. Okay? I see that I'm running a bit out of time with respect to my plan, so I'll skip one of the topics that I meant to speak about, which was text-to-speech. And I'll speak about dialogue systems to illustrate the move from rule-based systems to data-based systems. So the systems that I said were winning the Lubna Prize these days are systems which are very, very dumb and simple. They're built on rules. Things like this here: pattern, template, and then response. They're literally built on this. So they have a language for this. It's called AI/ML, Artificial Intelligence Meta Language. And maybe you've heard of ELIZA, which is an early example of these systems. Alice, which is another example of this thing. They're built on rules like, I thought I had a better example of this, but I don't. Let's say if the user says something that sounds like, what do you think about, and then anything. So you have wildcards, you have stars. All the rules are a bit like that. And so they fake human responses because they cleverly made huge databases of, vaguely sort of humorous or human-sounding responses. But indeed, they're only they're entirely knowledge-based. There's no training or nothing about data in here. By contrast, we have attempts that are made today with neural networks, which are entirely learned from examples of dialogues, which try and do the same things. They try and do dialogue. This is an example. These are examples of such dialogues. If you look at them, you'll see that they're not up to the task yet. So here we go. Machine says hi. Human hi. Machine says, could you please let me know what is the operating system you're using? Human, Linux. Okay, this is the issue with the system performance, Nasser tools. Human, huh? Machine, is it a Windows machine? Machine, we have Linux on your machine. Is it Windows XP or Windows 7? Human, I'm using Linux. Okay, but clearly things are not exactly working out right, and this is sort of state of the art for neural dialogue systems. This was published late last year by a Google team. In between, we've got systems which are the state of the art in industry, certainly. So this is an example of a dialogue system, an open source dialogue system, which is called RASA, which is also statistical, but it's, while this thing, the neural network system, sits here, the state of the art systems nowadays, they're still here, okay? So not entirely, I mean, there's a lot of hard-coded intelligence in there. So this is to say that, yes, so there are both ends. These things, rule-based, these things, neural network systems, but the state of the art, in this domain at least, is still somewhere in between. Now, in image classification, the systems that worked very well here, and they were based on a pipeline that extracted salient features from an image, malaxed them or massaged them together, and then did classification. So when the task is image classification, which I'm assuming here, we want to decide what this image represents. It's kind of like a church, probably. So the way these systems worked until 2012 was like this. It was by detecting salient features in images and putting them together and making classifications. And in detecting the features, there was still quite a lot of expert knowledge about colors, gradients of colors, edges, angles, and stuff like that. Now, in 2012, what came out is the revolution brought by neural networks, which led the state of the art to be to go from here, where it was before 2012, to here, entirely data-driven. ImageNet, it's an object identification competition that made the field, move ahead greatly. So every image in this data set is labeled. So here we have mite, container ship, motor scooter, leopard, Madagascar cat, cherry, mushroom, grill, and so forth. And that's the error rates on this competition. So you can see that this is 2010, 2011, 26% error. Boom, 2012, 16% error. And then it went down with the years. This is human. Red here is human. So we're doing superhuman on this task here nowadays. 2017 is the last result we have here. And this is when neural networks started to be put at work on this task. They're called convolutional neural networks. They're very different from what I described before, because instead of having expert-designed edge detectors and color change detectors and stuff like that, all these detectors are now learned from data. They're not pre-programmed, okay? What happens is that the best detectors survive in a way, and the bad detectors for edges and stuff like that, they get thrown away. But all this is based on data. So data meaning here couples of images and their labels. So those guys, those detectors that manage to do a good job for extracting these shapes and stuff, they get to survive, and the other ones, they're thrown away. And this is an example of a CNN. So it's a neural network just like the one I showed in the beginning with digit recognition, except that it's got many more intermediate computations than the two layers, the two hidden layers they're called in my first example. And in fact, this is an example from 2015. So this guy has got 22 layers of intermediate computation. And nowadays, the state of the art has got hundreds of layers of intermediate computation. Okay, so all this shows why there's this convergence between what people used to call AI and what is machine learning. Machine learning having to do with this end of the scale. Okay, it's about learning from data. It's not about writing hard-coded rules. It's exactly the opposite. Okay, so let's do a bit of a quick overview now that we've gone into this history stuff and in understanding this move from knowledge to database systems, what we can do. You give them an image, they can localize the objects, and they can say what they are. So they localize and identify them, and they tell you how confident they are. Another thing that they can do is object segmentation. So they can tell you not only in bounding boxes, but exactly pixel by pixel, what the shape of objects is. This is used in, say, in modern cameras. So when you take pictures and when that you have a face detector, then you can do things like keep the face clean and then blur the background artificially, and then that gives you a super good-looking photo because you have a portrait, essentially a professional portrait. And this is obviously useful for self-driving cars as well. What is a bit beyond the state of the art, but which is nevertheless useful, is 3D vision. So here we have an example. I show this picture to say this is a sort of synthetic set of data. And the point of this picture is to say people now work in this data-driven world. They work with tricks to produce data for the task that they're after. To do 3D object recognition, they will actually go and construct so-called synthetic data sets. So they will simulate 3D environments and, in video game rendering engines, and take pictures of 3D environments that they know, of which they know where the objects are placed in, and they will train computers like machine learning systems to answer back not knowing, only seeing the 2D representation, where the 3D objects might be in the scene. So learning things like perspective. So in a data-driven world, you need to apply these tricks, synthetic data generation, to have sort of big data sets. Obviously, it's very difficult to do. You can imagine doing the same data sets in reality. You need to take pictures and then register the 3D position of things. It's super expensive. So that's why people simulate it. Another thing that we do well nowadays is optical character recognition. And here again, if you think of it, you've probably all run through CAPTCHAs that ask you to transcribe photos, or maybe just this bit here, 1934, and transcribe the digits. So these serve two purposes, clearly. One is to check that you're a human, and one is to gather data from you for free to train OCR systems for OCR in the wild. So they're sort of clever systems designed to do exactly this. So you're performing work for free for these guys, and these guys will gather the data, and then they'll train OCR systems to do exactly this. Okay. Other things that can be done these days is pose estimation. So you have it's pretty accurate nowadays. So based on 2D videos, you can accurately estimate the position of limbs and joints of people. And so you can do all sorts of fancy things. You can detect what action they're performing. I think I have, I have a video, but you can imagine this guy is playing cello. You can see people playing tennis, and based on their pose, you can detect that they're playing tennis and so forth. Pose estimation in lips and mouth and stuff like that, tongue, teeth, is lip reading. Computer systems are better than humans, than professional lip readers. They're better than professional lip readers at lip reading. Nowadays, machines do it better. And one clever thing to have in mind about this task here is that it's very easy to get lip reading data, because what you have plenty of is TV programs with people speaking. So you have both the video of people speaking and the audio. You just separate the two sort of tracks, the audio and the video, and voila. You have the input to your system, the desired output, which is the audio, and you have plenty of such data. And this is why these systems could be built, because at the time then, 2016, 17, we had the machine learning systems that could deal with this data. Another thing that we can do nowadays is generate images, very high quality images. These people don't exist. They're high quality simulations of what people might look like. And they have been created from databases of celebrities, millions of images of celebrities, by a machine learning technique called GANs, Generative Adversarial Networks. And they're very high quality reconstitutions of photographs. They have the added advantage that you can sort of manipulate the images. So you can go from input images and tell the system, the generating system, blonde hair, swap the gender, make them aged, pale skin, make them look angry or happy or fearful, okay? All based on information that is learned from faces. You can also generate more funny things than just faces. You can generate scenes. So you can generate, based on this kind of drawing, you can generate realistic looking scenes of streets, because you need to go from, the data that you need is pairs of this and this. So if you have an image segmentation system like I showed before that works about well, then you can produce tons of pairs like this. Except then you go from here to here, while before we went from here to here, for which you need other data. You can generate, people play and generate facades, realistic looking. This doesn't exist. This building doesn't exist, right? The input to the system is, it generates windows and a door and stuff like that. This is a system that colorizes. It goes from black and white to color. So you can change videos and apply new styles. So this is a horse, quite obviously, and you apply zebra style on the horse. Between stripes needs to look realistic and stuff. The stripes need to be curved and blah, blah, blah. None of this is all learned from images of zebras and images of horses and going from one to the other. The same thing is applied to artistic creation, so has a lot of impact on creative jobs, clearly. So these are examples of, so we had zebras to horses, but we now also have examples of going from photos to painting styles. So this is a Monet style, a Van Gogh style for the same photo, right? Monet, Van Gogh, Cézanne, and the Japanese ukiyo-e style. So this is something that we can do all based on data, not learned. So the more data we have from painters like Cézanne or from, I don't know, Pollock, the more we can make systems like these. And that's a lot of fun. Okay. Another important application for, well, industrial usage is what's called super resolution. Image compression, video streaming, okay? You need to compress the images that go from a server when you're watching a movie or your favorite football game on your mobile. You need to compress the video, so video arrives on your mobile with a lot of detail lost. It doesn't look very good when it arrives on your mobile. And so a useful application to work on, and this is now going from research to industry, is working out the detail that has gone missing. And obviously, there's no magic. The detail is invented. No guy has sat down and said, ripples on water look like this, all. But instead, this is learned from many images of ripples in water and buildings and edges and angles and everything. Okay. Another thing that we can do well, and I'll be coming to an end after that, is going from images to text. So these are captioning applications, image description applications. So you have images. So this here is an image of a little girl sitting on a bench holding an umbrella. And the computer is asked to look at the picture and generate the caption. Data that's needed for this is tons and tons of pairs of this. Okay? How do you obtain such data? Well, either you do it web crawling wise. So you look at tons of websites and you assume that the text that surrounds images is sort of descriptive of the image. And then you say, oh, I found an image. I find some text surrounding it. Surely the text must be somehow descriptive of the image. So let's use that as training data. One option. You have very much data like this. It's for free. And then other option, higher quality but has a bit of a higher cost, Amazon Mechanical Turk. You have people who sit down and for 5 cents, they will look at a picture and type in a few words to describe the picture. A great thing with these systems nowadays is that you can look into the engine, if you will, and you can find out what part of the image they're looking at when they're spitting out what words. So here we have blue, red, and green. And in the image, we find the points that they're looking at when they generate the blue, red, and green words. So here, for the little girl thing, example there, when they generate girl, they're actually looking at the girl. Wow, it works. Sitting on a bench, they actually look at the bench. So this is why we have red here. Holding an umbrella, and yoo-hoo, it works. Umbrella is in green when the system generates the umbrella word. Another example of generation is going the other way around, going from text to image. So this is a new kind of task. It's sort of from the last 2 years, probably. You start with a description, and you generate an image that corresponds to the description. And this set I like because it shows you where it goes wrong. Okay, so you have examples here of a small bird with a black head and wings and feature with a black head and wings and features gray wings, whatever the sentence is a bit malformed, whatever. So you have things that look like birds, but if you look at them in detail, they're kind of monsters. You don't really want to meet with a bird that looks like this, presumably. Okay? So they look like it because they've been trained on realistic images of birds, but no one has really told them that a bird has a back and a front and that the beak sits on the front and stuff. It's just by statistics that the beak happens to stand in front of the bird when the thing generates it. Okay? And that's what explains these glitches, these errors. So I've told you a lot about what the state of the art looks like nowadays. What I want to spend a couple of minutes about, forgive me if I'm running out of time. I'm probably over time already. Off we go. We're in the kingdom of open possibilities now. Having run out of time, the night is ours. I want to tell you a bit about what AI cannot do. Basically, I would say what it cannot do is all the rest. That's a lot. Okay, so there are some things, there are many sort of detailed things that I could tell you, but they're not super interesting. Many things that cannot be done are revealed by the errors in these systems. So when you run into demonstrations, say a startup shows you what they can do, you know, their AI can do this and this. What is interesting to ask is, oh, can you show me error cases? Okay, and when you see error cases, then immediately you understand where the limits, where the probably narrow boundaries of the system in question are. This is the first question to ask, I would say. So what, can you show me like typical error cases? Where does it go wrong and in what fashion? And there you see, okay, it can do this, but it doesn't do all the rest, and that's where the possibilities stop. And as you have seen from my examples, they're all pretty narrowly defined tasks. And this is the state of the art today, and it would be wrong to tell you anything else. Many people will tell you everything else, but they're usually wrong. Or they have a vested interest in saying that they can do, or their systems can do other things that they actually can't. All that we can do reasonably well nowadays are these narrow tasks. We can't do anything that has to do with common sense, reasoning, abstracting concepts, generalizing from domain to domain. Again, notwithstanding what maybe some AI vendors might tell you, okay, because they will tell you they can do such things. But usually, if you look at the examples or at the exact thing that they do, then you'll say, well, you know, no. Right, so this is the sort of frontier of where we stand. And if I had to tell you where we are going, I could tell you of one typical path that we're taking. So what happens usually, let's see. What happens usually is we're going from systems that do so like, is that right? No, it doesn't, so I'll write it here. That goes from small tasks, like the ones I've shown, tasks that are like image captioning or going from audio to words or from English to French translation and so forth. I'll call them small tasks, and that sort of put together several small tasks. So maybe you have a system that goes from audio to word, say French audio to French transcription, and then French transcription to English text, and then English text. You have a text synthesis system that is able to produce some English spoken audio, and then by piecing them together, you have a system that does so-called speech-to-speech translation, right? The way it goes is that usually you have initially like these small bits you had, so like in the early 2000s, working in the early 2000s, and by piecing them together, now you have systems that do the entire chain. And what happens, the next step of the evolution in AI development is that you have systems then that start doing the same task end to end. Before in speech recognition in the 90s, you had systems that would go from speech to a sequence of phonemes, so symbolic representations of sounds, and then from sequences of phonemes to actual strings of words by using, very usually by using dictionaries that would, a pairs word, like orthographic, string of letters, the word, pairs of that and of sequences of phonemes. And the thing would go and start from the phoneme representation and try and match it to sequences of phonemes it had in the phonetic dictionary. And then say, okay, these are the sequences of phonemes for 5, so it's probably the word 5. Okay? Nowadays, systems are end-to-end in this industry, and they no longer represent phonemes inside. And this is a big victory for AI. Humans invented phonemes. Linguists invented phonemes. But we don't really need linguists in speech recognition research teams. We can do without look. And he showed systems that did without phonemes. Okay? It literally learned from sequences of audio signal and words and went directly from one to the other. And this was a big step in understanding that this was the way in which AI would develop in the future. The problems to advance the field of AI, the sort of problems that people are thinking about these days are ideas to tackle the problem of domain transfer that I was mentioning before. Domain transfer meaning if I learn something about cars, about recognizing car models in images, does that somehow allow me to do progress on the task of recognizing buildings or recognizing animals? So how can I use a system that I've trained for recognizing cars and using in recognizing animals? If I have this possibility of transferring from domain to domain, then I can make a lot of progress, and then I can sort of maybe generate new data, by having humans just check, not generate, but check predictions of a machine. Amazon Mechanical Turk people, you present them with what a computer predicts in the way I've described. Maybe sometimes like 70% of the time it's right, but 30% of the time it's wrong. Instead of having them type in the thing all the time, they only correct the thing 30% of the time when they see it's wrong. And by this sort of virtuous circle, you produce more and more data for this difficult domain. So this transfer learning idea is one that is researched heavily and that people think will work well, also because we think that this is how people work. We learn to do things. We have general skills in a way that we learn from some tasks, and then we're faced with new tasks. And the skills we have learned, we apply on the new task, and we perform reasonably well at the new tasks, even though maybe we've never done them before. And in the same fashion, what is trendy is unsupervised learning. I'm getting to a stop. Unsupervised learning is learning from data that does not have the label on it, that does not have the response, the desired response on it. It's just signal. It's just images, maybe. It's just video. You have plenty of video on YouTube. Just by looking at video, can we train a system to understand, what objects are and how they move? And that objects usually, when they appear on a video, they don't just from one frame to the next dissolve in purple mist, okay? But instead they sort of stay compact. And when you see an object on a frame, then the next frame you'll find the same object. Maybe it has moved in the next frame, but it's still there, and it hasn't sort of disappeared all of a sudden, okay? So this kind of knowledge about the physical world, can we learn it just from looking at video? The same way audio, the same way text. Can we learn things from just looking at what happens out there? I think that as a field, we're headed, obviously there will be such big disruptions. I haven't mentioned quantum computing, but presumably this is going to change the game as well. It's coming. And so what we're looking at is probably what's yet to come is the most formidable bit of the history of AI. It's not, I mean, surely what we've witnessed so far is just the most boring and the most smallest steps. I think the most formidable things, the most disruptive things, they're yet to come. Thank you.